sensors at Worth. He began his career as a patent examiner assistant at the European Patent Office before joining Worth Electronics in 2018 as a product manager. At Worth Electronics, Ninad is responsible for sensor components with a focus on pressure and temperature sensor technologies. When the presentation is done, we're going to have a live Q&A with Ninad, so you can submit your questions at any time during the session using the Q&A box that you can see on the right-hand side of your screen. We will provide the attendees with a download copy of the presentation, and you'll be able to get that in the handouts tab that you can see on your screen there. At the end of the session, I'm going to be announcing the two winners of this session's giveaway. So thank you, audience, for joining us. And with that, I'll hand it off to Ninad for his presentation.
Thank you very much. I will share my, hope you can see my screen now. Hello everyone, and thank you for joining the live webinar today. I'm Ninad Mehta. I'm product manager at Virth Electronic, and we are going to have a look at today's webinar, Smart Pressure Sensing in HVAC System. And the focus will be on how sensors or pressure sensors can be used in predictive maintenance in HVAC systems. Let's have a look at the agenda. So the agenda, first we will go through what is HVAC, heating, ventilation, and air conditioning. Then how can predictive maintenance be used in the HVAC systems, and especially the focus will be on the pressure sensors in the HVAC systems. We will then go on with choosing the right sensors for your HVAC applications, basically which type of sensors to use, a pressure sensor or a flow-based sensor, analog or digital sensors. And in the end, I would like to introduce to the Virth Electronic pressure sensors portfolio and how we can support in your applications through customizations. So let's get started. HVAC, as the title suggests, and heating, ventilation, and air conditioning is quite known to everyone and should be very much familiar. Everyone should be very much familiar. What it does is it does what, as the name says, heating, ventilation, and air conditioning of the whole building or a whole apartment, wherever you are using these kind of HVAC systems. Usually they are very common to be used in residential buildings nowadays, but in the past they were very much common to be used in commercial and also factories or also hospitals and big labs where you need to control the indoor environment. So basically with the heating and air conditioning, you can cool your apartment or the place down or heat them up based on your requirement, and also flow a very clean air throughout your building or indoor area. It's a whole HVAC system is a very, very big system. You see those big vents and the condenser running outside the apartment or building as well. And there are the whole HVAC system is made of many different subcomponents. Mostly, if we can see, the major components of the whole HVAC system would be the thermostat that you see inside your building or an office, to see what is the current temperature, what is the current humidity, or and so on. To cool down the air or to heat up the air, you have a condenser or heating element or heating coil, which will where the air will pass through, and then it will be cooled down or heated up based on the requirement. The compressor to provide compressed air, so the motor, so as to say, and then there are fans to regulate those air throughout the vents. And in the end, another important part is the air filters, where the air passes through and you get a very clean air, basically. So these are the major components of the HVAC system, and the whole requirement nowadays is regularly is that how you maintain these HVAC systems. You need to repair them time to time, and you might need to upgrade those systems. A very important fact why upgrade is needed is that even today, more than 50% of the buildings which were made, which are now available, are built before 1980s. So the HVAC systems that these buildings have are either outdated or they are quite old and they need to be upgraded at some point. The older systems are not that power efficient, not that working not that efficiently overall. So they consume a lot of power and they need to be upgraded so that they can be more energy efficient in the end. And as the time goes by, they are required to repair or there are some breakdowns. A very interesting research from the government of Australia that you see is the energy consumption of an office building, where you see the the highest energy consumption is consumed by an HVAC system. And if you break down the HVAC system, where the most of the energy is being consumed is from the fans, cooling and heating, and also certain amount also is consumed from the pumps. So basically, it is very much important that we make these HVAC systems as energy efficient as possible. There is another interesting news which is very recent, where the because of the malfunction in the air conditioning system in one of the hospitals in Chicago, that they had to evacuate all of the patients, and because the temperature were not being controlled and they were soaring very high. So these are the things that we need to avoid or needs to be avoided in a running system, where you your focus for the whole HVAC system in the end would be that my system should be as low maintenance as possible. When there is an issue, my downtime should not be very high, so low downtime. The hospitals cannot afford to be closed for a longer period of time. They must be energy efficient. Higher energy, lower energy consumption means that in the end the system is very cost effective. And in the newer generations, HVAC systems needs to be more and more interconnected so that these subsystems talk to one another continuously. So in the end, we need to in order to fulfill these kind of requirements, the system needs more and more data about the environment, because in the end these systems are always monitoring the environment. So the environment values, for example, you need monitoring of the environmental aspects: pressure, temperature, humidity, or even the vibration of the motor, for example. By doing this continuous monitoring, it is possible to get more and more information about what is the status of the system, and also control the indoor environment through monitoring these parameters of the environment. How can we do this is a very simple answer: through sensors. Basically, sensors can be eyes and ears of the whole HVAC system. So the sensors can sense the pressure, the overall humidity or temperature of the room or of the systems that are part of the HVAC, or even, for example, a vibration of a motor or a pump. So the sensors can be used to get more and more data. The more sensors we use, the more data we can get. And how the continuous monitoring will help us in terms of the whole HVAC system, we can see in the next slide. So basically, before we go one step ahead, what can we achieve, or what are we doing right now with the whole HVAC system, is how do we maintain them. So very roughly said, there are three kinds of a maintenance system that are being used. The very basic one is the preventive maintenance, which is being routine checks. So basically, you have a person who is checking the systems if they are running correctly or not at every fixed interval, every 2 months, 3 months, or every 6 months, as per the requirements. So these routine checks are usually time consuming, and that they cost also a bit more. Another type is that corrective maintenance. So basically, this means that when it breaks, you are going to go and fix it. So the drawback of this is that there is a very high downtime, because the system is already not working, and then you are going to find the problem where the problem is, and then you're going to fix it. So this results in a very high downtime, as we saw in one of the examples before, that the downtime is also not that good to have in the end. So in between is the predictive maintenance, where you get an access to the real-time data of the whole system, and you do with this data, you do continuous monitoring. And that's how with the sensors we can enable these systems to have a predictive maintenance. So in the end, if we use this kind of sensors to capture the environmental data in the end, then we can capture and save the data. After capturing the data, we can also transfer the data. So basically, to make this system interconnected, we can choose one of the protocol to send the data wirelessly from point A to point B wherever we want. Then with sending the data, we can collect the data through any cloud server and then have an access to this real-time data through the cloud monitoring system or wherever your dashboard is. And with that, you can have and you can ask these questions: is the data that you have, are they normal, are they within the expected range, or am I seeing any abnormal behavior? And when you have this kind of system running, then you can have a real-time monitoring and continuous monitoring of the system. And whenever you see any abnormal behavior, you can alert the system technician to have a look at it, to have a look at the problem and try to resolve it before the error or where before there is a breakdown. And that's how with the smart or with the sensor systems you can enable the predictive maintenance in the HVAC systems. As I mentioned that we are going to focus on the pressure sensors, so we are going to only limit our focus today for the pressure sensors. And how can pressure sensors be used in the HVAC systems or are already being used in HVAC systems? There are some of the important examples where we see the use of pressure sensors. So one of them is the ventilator and fan control, so basically a flow control. So basically with the Bernoulli's principle, you can use a differential pressure sensors on the either side, two nozzles on the either side of the fixed orifice where you make a pressure drop. And based on that, you can have a difference of pressure between the two sides to control the flow or ventilator or the speed of fan continuously. Another use of pressure sensor, differential pressure sensor, is that to have a filter monitoring system where you can check the health of your filter by checking the pressure on the either side of the filter. And whenever the filter is not working, then you have a more pressure on one side, and this could be meaning that your filter is being clogged. Another one example is the static air pressure control. Basically, here you use the differential pressure in a sort of a gauge configuration where one port is being always open to the air and another port always checks for or monitors the pressure of the air vents. These kind of applications are also very common in clean room or in the hospitals where the ICUs or operation theaters, where the air pressure inside these rooms needs to be different from the lobby so that the contamination doesn't go in. And another example is the variable air volume or VAV or damper control systems, where also similar of a flow principle, you can also use the damper control with the differential pressure sensors. So these are the examples where differential pressure sensors can be used in the HVAC system or are already being used in the HVAC systems, and they enable more level of monitoring or an active level of monitoring. How can we utilize them for the continuous monitoring or the predictive maintenance? Let's take one example in more detail: the filter monitoring. Basically, we all have this in HVAC systems, the filter where the filter is placed on the inlet of the building, where the air from the outside comes in, filtered, and then clean air is distributed throughout the building. So the filter is basically acting as a lung of the whole commercial or whatever building where the HVAC system is being used. And since the whole COVID, the indoor air quality has been of very important. Everyone is aware about it. We also, on the other hand, spend most of our 70% approximately our life in indoors, and indoor has more air pollutants than outdoors. So the role of a filter becomes more and more important, and everyone is being more and more aware about this. As mentioned, we need to change the filter as it is being used. So basically, what happens if you change the filter very late or it becomes dirty, clogged, and even if you don't change it, this reduces your overall airflow. Basically, the clock filter will not let the air pass so easily, so this becomes disadvantageous in two ways. One way is that since the air needs to be pushed through the filter, the compressor needs to work more faster, and that is also not so efficient, and this consumes more energy. And on the other hand, you have a poor indoor air quality, so basically you are incurring more costs and also reducing the air quality indoors. On the other hand, you don't want the filters to be changed way too early, which increases your costs, and it's also not environmental friendly. So there are pros and cons basically, but then you need to know when is the right time to change filter, and it is also important to have this known to you. So as mentioned, with differential pressure sensor across putting it across the filter, we can have a very accurate filter monitoring system. So basically, as the filter is being clogged, the pressure here is increasing with the time, and at some point when in a normal behavior, so as to say, there is a more or less a linear pressure drop when the filter is being clogged, but at some point there is a exponential increase in the pressure drop between the port A and port B, and that's where we can have an alert sent to the technician that it's now time to change the filter, because based on those information of the pressure drop, we can predict that maybe in 4 weeks there is a high chance that filter gets completely blocked. So maybe when the filter is around 80% block or 90% block, we make the decision to have the filter changed. So basically this becomes in the end a smart air filter monitoring system, just by introducing the kind of a sensor inside the system. And if the sensor talks to the microcontroller, and from microcontroller it can go have the information on an IoT device, IoT end device, and this data is available at 24/7 to the end customer. Another examples are the fan failure or leakage detection, as we saw for the airflow monitoring. If there is a leakage somewhere in the vents, then in the normal operation, you see that the airflow or the pressure values in this through the sensors from the sensors are more or less very linear. But whenever there is an event of leakage, then the pressure starts to drop slowly, or even you see the same performance changes in the compressor or the motor, where the compressor needs to work more than what should be the normal operation. And that's where you see these abnormal behaviors, and this could be also alerted that okay, there is a leakage in the system, where I need to take active action and find the root cause of or where the root cause is, and then stop it from malfunctioning. Another example is also similarly for the motor control or fan failure. In the normal operation, you have in the green part there the pressure values are more or less stable because the flow is stable. The fan works normally. But if the fan health is deteriorating, or fan is not working properly or behaving abnormally, then you see the abrupt behavior or abrupt pressure drop or increase of pressure throughout the operation. And that's where an alert can be generated, because this abnormal behavior of fan is an indication that in future at some point the fan might fail. So even before the whole system collapses, it would be a good information to have and take an action for the fan degradation. So these are the ways where the sensors, especially the differential pressure sensors, can be used for monitoring the HVAC systems, and also enabling the conditional monitoring to prevent extra cost or extra downtime. But we saw most of the examples where we see that pressure sensor is also being used to monitor the flow. And then the question comes, which is a which is the sensor that I should use in my system. So this in the end also depends on what type of application you are having. On the left side, you see that conventional pressure sensor with a membrane based system. So this is basically the force being applied on unit area, and that's what is the measure of the pressure, and that's how the pressure is being calculated. And on the right hand side is the another principle where you are measuring the flow. In modern flow based sensors, they use a small heating element or a very small heating coil, and there are two resistors which are temperature dependent, and basically when the airflow flows on top of the heating element, the hot air disperses, and one heating element or one resistor and the other resistor will have a different values, and based on that we can calculate how much is the flow in the flow based sensor. So there are pros and cons for both type of sensors. For example, in the flow based sensor, the air or the gases flow through the sensors completely, so you need to calibrate each and every gas that you are going to use in the end. So for air, basically, because each gas has different density, and based on that the air heats up or cools down, and that's why for air this doesn't play a very big role. But for some coolant or some different gases, they need to be once more calibrated based on their density. Mm, Based on the power requirement, the heater here there is a heater which is constantly on, and it needs to be heated up 24/7 or when the sensor is in operation. This consume a little bit more power than normal membrane based sensor. But on the other hand, when you are having a very low flow or low pressure applications where you need to measure a very smaller change of pressure, then the flow based sensors work very effectively compared to the membrane based sensors. On the Also, on the other hand, when in the HVAC systems, you see that the air is not always 100% clean. So there are small dust particles. So because of the flow sensors, the air flows throughout the sensors. There is a risk of the sensor getting clogged. And if the sensor gets clogged completely, then the sensor will stop working. In the MEMS or the membrane based sensor, the it's not usually the case where the sensor gets clogged. If there are dust particles, they are deposited on top of membrane, which in the end adds some drift to the sensor or the pressure values afterwards, which can be recalibrated via the end system. Basically, these are the pros and cons of which type of sensor you are using. One more difference is the characteristics output. So basically here the flow element, because it works on the flow principle, the output characteristics are not linear, but here the membrane based sensor has linear output characteristics, which also helps in the end when you want to have a digital data output. So this is a big picture where different types of or the flow type or the pressure or the membrane type sensors can be used. Today we are going to focus on the membrane based sensors, especially the MEMS based pressure sensors. So MEMS stands for the micro electromechanical systems. So these are a very small systems where you have a very thin membrane. So there is a silicon substrate, and the silicon substrate is etched from the bottom side, and the etching is stopped via chemical process when you have a very thin layer of silicon which is left. So basically this is a freestanding silicon substrate. You can imagine a trampoline, basically, where the trampoline is freestanding through the rims on the sides, and this is exactly like a trampoline. And on the sides then we deposit some piezo resistors. So the piezo resistors will change its resistance based on the stress that it is exerted upon. So when there is a again, we imagine this trampoline structure, and then there are 4 piezoresistors on the sides, which could be the springs of the trampoline, so as to say. And whenever there is a pressure from top side or someone jumping on the trampoline, you will have these piezoresistors either in the tension or compression. So what we do is then in the end, there are 4 piezoresistors. We make them a normal Whiston bridge configuration, and whenever there is a stress on the from the top side, the resistance changes. And in a normal operation, the Whiston bridge is basically when we supply with some voltage, the bridge is in a normal stable condition. But whenever there is a stress, the resistance changes, and that's why the bridge will be in imbalance, and then you will have some output voltage drop. And this output voltage drop is directly proportional to the stress or the pressure being exerted on top side. So basically the pressure will be converted into electrical output of millivolt, and that's how the whole MEMS based piezoresistive pressure sensor works. The change of pressure will lead to the change of resistance, and change of resistance leads to the voltage drop of the Whiston bridge, and that's exactly directly proportional. So when we get an analog output which is not compensated, not calibrated. We don't know yet how much stress or how much pressure will lead to how much of millivolt output. But in the end, we have a functional pressure sensor. And what are the benefits of this technology is that your system is very linear, as we see that it's using a Whiston bridge and with a resistor, so the output characteristics are linear, and that's why it's easy to produce. And also there are no complex structures, and you can mass produce it very easily at low cost. The drawback, however, because of the piezoresistors, they are sensitive to temperature changes, and this can be also, we will see in the next slide that this can also be eliminated by using specific ICs. So what we see, this kind of piezoresistive MEMS-based pressure sensors in the market today, and this is an important information to see and compare what different types of MEMS-based pressure sensors that we see today in the market. The very basic ones are the MEMS cell itself, what we saw in the previous slide, which is just the Whiston bridge, very small bare silicon die. The output is here non-compensated. It's also not calibrated. You have a very small millivolt output, so you might have to have an electronic circuit on the side of the output. So basically you will have to amplify the millivolt output, and then you will have to multiplex or then convert them to analog to digital output based on your requirement. Or even, since these are usually available in bare die or package die, you will have to design the whole PCB for that. Another type of the sensors are amplified sensors. So they have basically the same MEMS cell, but then you already have inside the package an amplifier. So you don't no need to have your own amplifier circuit, amplification circuit, but this is already included inside the packaging. And also some level of compensation and partial calibration is already done through laser trimming resistors. So basically during the production, at a 25 degrees or 30 degrees, we do the correction of the values so that the values are stable and calibrated for certain temperatures. So if the factory calibration is done at 25 degrees and your end application works at 60 degrees, then it is very well possible that the output at 60 degrees is not going to be fully calibrated what we do in the labs at 25 degrees. So this is a kind of a better solution, or so as to say, in terms of the calibration. It is partially calibrated, it is still an analog output, passively compensated, and you get it also in the package die. The last one is the integrated sensor. So basically, again, you have the same MEMS die, but then instead of single electronic components, you have a dedicated IC, where on the IC you have integrated DSP, integrated memory, and also you have analog to digital converter, and also the whole logic for the digital output. So basically, what is the benefit of this kind of sensor is that you already have some memory, and during the production process you can directly store some calibration algorithm or calibration parameters inside the sensor. whenever you put the sensor in operation in the end device, this calibration algorithm is always functional. So in the end, you directly get your digital output via digital interface I2C or SPI. So you can directly plug this sensor directly with your host controller and start receiving the fully calibrated and fully compensated temperature pressure values. This kind of IC usually also have an on-chip temperature sensors. So the compensation of the temperature can be also done during the production process, and this is how the disadvantage or the drawback of the piezoresistive temperature dependency can be resolved. So basically, during the production process, the whole chip is usually calibrated from the minimum temperature to the maximum temperature as per the requirements. So in the end, the output that you get is independent of the temperature that you are deploying or your system is going to use. So this is the most complex type of sensor. So you see that you have in the market available from a normal sensing cell to an complex integrated sensor system, still packaged in one single package. But in the end, this is a whole sensor system, not just the measuring element, but also the small IC inside. And then the question again arises for such kind of applications, whether which kind of pressure sensor I should use for this kind of my HVAC applications, whether I should deploy an analog type of sensor or a digital type of sensor. Again, this is also dependent on the end application. How do you want to and where do you want to deploy the sensor? Where there are higher accuracy requirement, then analog sensor works more in a better way, because then you are not losing the data through or through to analog to digital conversion, or also there is a lesser noise, so your accuracy becomes a bit more than the digital sensors. But on the other hand, you have lower current consumption and higher resolution thanks to the new ADC or 24. Usually newer sensors comes with 16 bits or 24 bits of analog to digital converters, and most of the IC also have on chip temperature sensor built in, so you can already get the temperature information from this sensor as well. Also, we discussed the requirements from HVAC, that the systems are usually interconnected and talking to one another. So for those requirements, you need a digital type of sensor where you can directly plug the sensor with the microcontroller and start receiving the calibrated digital output. Or also these systems are now also enabling or used for the IoT applications, or requirements are always that they should be IoT ready or IIoT ready, where digital sensors play a very important role, which also in the end saves your other components on the BOM. When you are using an analog sensor, then you will, in the end, for the IoT application, you will need a separate A to D converter, multiplexer, and amplifier. And then in the end, you have those analog parts designed with the MEMS analog sensor, and in the end it could be very well possible that you will have to recalibrate the whole system once again and then deploy it in the IoT infrastructure. So having a digital sensor makes the life on the other side easier, that you already get the fully calibrated and fully compensated digital output through your microcontroller. So based on those requirements, the choice becomes much easier whether to use an analog sensor or a digital sensors. How can one more interesting aspect where a smart sensor or a digital sensor can have a very low power consumption is, you have, for example, a sensor which is directly interfaced with a microcontroller. So basically it is sending the pressure values through microcontroller, and through microcontroller or your chip, via you are sending your data, for example, let's say for through Wi-Fi protocol to the cloud, and you are having access to this cloud server. So for any kind of monitoring, you have, for example, a threshold algorithm built in on the microcontroller side, that hey, my pressure drop should not be more than X value. If it is dropped more than that, then the microcontroller sends the alert or the system to the cloud server, and here I have a bigger behavioral algorithm built where my alert is being flashed, where my problem might be or where I have to look for an abnormality. What happens here is you still have the continuous monitoring for maintenance and all the benefits that we saw for the real-time monitoring. But here the sensor will be communicating with the microcontroller continuously to see if my threshold is surpassed or not. So my microcontroller is active 100% of the time, which consumes a bit more amount of my current. And on the other hand, I'm sending a very high amount of data also to the cloud. So this also requires higher processing power and also requires higher energy. But what if this in the same system the threshold algorithm is moved from the microcontroller or to the sensor itself? So you have a more edge computing doing directly on the sensor. This is possible because now the sensors already has an IC built in, it has a memory built in, and it has its own intelligence. So the sensor will then send an alert only when the threshold is surpassed to the microcontroller. So how can this benefit is that most of the time your microcontroller will not have to ask for the data on a continuous interval, but on the other hand the sensor will send the data when the threshold is passed surpassed to the microcontroller, and only those data needs to be sent to the cloud for the alert. So this is, and in the end results in better performance because your microcontroller is active less than 50% of the time, results in a lower current consumption, and you are also sending lesser data packets to the clouds, and that also results in a better energy performance of the overall system. So this kind of sensor will help you also in overall better energy consumption of your system as well as the whole HVAC system. That was the whole overview so far of how can a sensor or a smart sensor can influence for your HVAC applications. Let's have a look now at the Würth pressure sensors and how can they be utilized for such kind of applications. So what we have now in Würth electronic portfolio is the pressure sensors that start from as low as zero point 0.1 kilopascal and go up to 1500 kilopascal, so more or less up to 15 bar. We have around 6 to 7 pressure ranges, which is a fixed configuration. They are all available at stock, and for evaluation we also have an evaluation board. These are all sensors with digital I2C and SPI interface, and they work on either 3.3 volts or 5 volts. They have a built-in temperature sensor and also analog to digital converter, which is of 15 bits. So basically, these are all fully factory calibrated sensors with digital interface. So these are suitable for all the requirements that we talked before for interconnected sensor networks or interconnected system. Enables also the real-time monitoring, and you can also by connecting them to a microcontroller or and directly a Wi-Fi or a Bluetooth module, you can also have the data sent wirelessly from point A to point B. So this is the whole sensors that we have already available. But if these are the sensors that are not suitable for your requirements, then we also have customized or individualized sensor solutions, which for example if the fixed pressure ranges are not suitable for your application, then we have the a possibility to change those pressure range, change the voltage level, or even have an additional digital interface, or even have this alarm functionality directly enabled on the sensor level, on the edge level, which helps also better power consumption. So this is also a service which is being provided from us for the applications that you might have special requirements for. And to have the prototyping faster. We have two different kinds of nozzles or the housing available. So this one with the straight nozzles, we have it for manifold mounting where you can design your own adapter, or with already the barbed nozzles where you can directly plug in the tubes and have a robust connection. We have also an evaluation board for the straight part. We have an additional adapter on top with the O-rings and sealing. So basically these are already being tested up to 15 bars. And we can also have this kind of adapter available as a design for you to design on your own. So the CAD files are also available. An important aspect here is also which kind of adapter that you might want to employ in your system, because for the manifold mounting, or we always recommend that adapter to be placed on top, because it gives you a better mechanical stability, because your tubes are, when they are directly connected to the sensors, there is a very high amount of stress. It is being transferred to the solder joints, and solder joints are made to withstand an electrical stress rather than mechanical stress. So this gives you an additional safety also against the leakage or dust which might get inside. So this could be one added level of safety through the then adapter. This CAD files for the adapters are available on our website as well, so you can have a look at that to modify it. You can choose them, or if you want as it is, those are also available from us for your rapid prototyping. That brings me to the end of the webinar, and if you have any questions, feel free to ask now. That's all from my side. Thank you very much for your attention.
Excellent. Thank you so much for that great presentation. And I want to let people know that there's still time to add some questions if you want to, so please do. With that in mind, my camera's being a little funky, so I'm going to leave mine off for now. But are you ready to answer some questions? Nenad.
Yeah, let's get started. So,
okay, first question. What role does edge computing play in enabling real-time monitoring and predictive maintenance in HVAC systems?
That's what I mentioned in one of the slides, where you have edge computing, where you have more power on the edge device rather than on the microcontroller side. So this gives you more room or more breathing air for the your host controller, which is usually the most active part when you are communicating with 5 or 6 sensor imaging, being having on with one microcontroller having more than one sensors always communicating, rather than having more power on the edge, where you have this possibility to directly program those, so as to say, these threshold values or these intelligent values. Then only basically the microcontroller will have to poll whenever the sensor sends some data. So this will have a result in the end of a faster reaction time and also lower current consumption of your overall system.
Yeah, because it's right there at the edge. Yeah, gotcha.
Yeah.
Next question. How do you compensate for environmental variation pressures, for example, like higher altitudes?
That's a good question. But here, when we are talking about the differential pressure sensor, whenever, even if you take the sensor at a higher altitudes, there is a differential pressure sensor, the thin membrane. So when two ports are open to the air, you don't need to have any compensation for those kind of systems, because they are like a open system, and when you put them inside your application, they become a closed loop. So basically for those applications, the environment doesn't play a role. In this case, when we talk about the absolute pressure sensors, they are like a barometric pressure sensors, where you have the range from around 300 hectopascal, 300 millibar to 1300 millibar, which is quite wide. So for the differential pressure sensors that we have, we don't have to compensate those values. But could be that in the end application, even if it's not a closed system, then you might have to do it through the host controller. Otherwise, there is no requirement.
Okay. Next question. I think you mentioned like the idea of some DSP on the integrated chip. The question is, what are the advantages of on-chip signal processing and embedded algorithms in HVAC sensor technology?
I think this is the similar in the direction of the edge computing. So on chip signal processing, as I mentioned, that when you have the signal processing directly done on chip, then you save at least some of the components on your BOM. You might not have to have a processor separately for only to compensate these analog values, or convert those analog values digitally, or save those values at in E square P ROM, for example. So these are all the benefits that you can achieve. And also we saw some examples where you have this alerts generated when there is a system leakage, for example, or a filter is clogged. This can directly be generated from the sensor itself, rather than you send each and every data to the microcontroller and then build an algorithm and recognize that now my system has a filter blockage. So basically this gives you more power directly on the sensor side.
Got it. The more power, the better there, yeah. Next question. Are the sensors suitable for liquid media?
So the sensors that we have in our portfolio right now are only suitable for the clean and dry gases.
Yeah.
But there are certain ways that you can make this available also, or suitable for the liquid media. For example, there are some gel coatings that we can put on the electronics, so that the whole electronics is secured, and then you can use those for also liquid medias. Or also some perylene coating is also available in the market, where you can say secure your electronics, and it doesn't influence what type of um, media is being flown. For HVAC systems, the most common is the condensation of the air, where
Yeah.
you have some water dropping inside the system. So this kind of to achieve a better solution, then there are some filters available which can not pass the humid air through it, so it will filter out the air. This will result in the end to some drifts, but this can also be compensated very easily through the host controller.
Oh, good. Okay, gotcha. How often do sensors need to be calibrated?
As mentioned, the sensors do not need to be calibrated once they are put in the end system. It could be with the time, or we see that these are the MEMS or membrane-based sensors. It could be very well that there are some dust particles or some contamination deposited on the membrane, which will result in maybe some drift, or the values not being as accurate. And usually these are linear drifts. This can also be compensated on the end application through, I don't know, every yearly or every 2 years, when there is a maintenance happening, then this could be also compensated very easily. So the sensor is not going to need any active calibration every 6 months or every year,
Yes, that's
ideally.
pretty long length. Yeah. So you mentioned early on, there's a question that you mentioned. You talked about data transfer stuff, wireless, things like Wi-Fi and LoRa. Are there any of those wireless protocols that are particularly well suited for transferring HVAC sensor data? Like, is one more reliable in this application than another?
I think that is also dependent on what type of protocol that you want to use. So for the home or the industrial buildings nowadays, LoRa is being utilized. In Europe we have 868 megahertz. I think in the US it's 915.
Mhm.
Depends on that requirement. The sensor is suitable for all of those in the end, because usually you have the I2C or SPI interface, and the LoRa or the Wi-Fi module already have a
Yeah.
controller that can
Mhm.
get the data through I2C or SPI interface. So in the end, it will depend what kind of protocol that you want to utilize. So what are your requirements? How much range do you need? How much throughput do you need? And based on that, you can choose. But in the end, these are suitable for all of them.
Gotcha. It's a question about, I guess, the scale of these things. For small residential or condo HVAC systems, do you see real benefits in adding smart pressure sensors with built-in algorithms, or is that level of intelligence really just suited for like large commercial systems?
Ideally, yes. For you're right. The large commercial buildings or the big factories or the hospital systems where you see more or bigger complex systems where you cannot afford to have the higher downtime, there the systems are more suitable. But in the end, the sensors are a very small part, and the whole system of the whole system. And nowadays, more and more small residential buildings are becoming smart, so newer buildings are having these kind of systems as well installed in the Europe. That's what we see. Also, we see some of the customers complaining, then even the private residential ones are never using or changing the filter
Hmm.
throughout their whole life, and
Yeah,
they go by, or these kind of things, and now they are becoming more and more aware. So employing this kind of sensors is not that complex if you see in a whole overview. But first step is that more and more industrial systems are being converted to this IoT based systems where you have continuous monitoring.
got it. So a lot of next question is some microcontrollers these days have like NPUs on chip for doing like AI and machine learning. Is AI something that would make sense in this type of predictive maintenance applications, HVAC?
Could be there is it's an interesting topic. I think we see that for example the vacuum cleaners or in the end they work in the similar way where you they can detect where
Yeah,
based on the usage, so how much I'm using my system. Based on that, I can predict already that in 6 weeks my filter will need a change, so I will already get my engineer or
yeah,
the technician ready with the parts if they are not available. And this gives a very well overview to also the maintenance companies who are doing this regularly, that they have this data, and they can continuously
yes,
look at this, and then make sure that there is a very efficient changeover or no downtime. So this is a very very good approach for the future. I see we have even some tests done for vacuum cleaners to have the filter monitoring and to detect
oh, okay,
at what
yeah,
usage you can predict the filter being clogged overall for the vacuum cleaners. So this is something that could be very well, I see also coming to the HVAC systems. Also, you have the new robotic vacuum cleaners which can detect also which type of floor you are using, how much is
right,
your
yeah,
usage, and then they give you directly a notification. It's now time to change your filter, or it's now time to change your bag, it's full. So
yeah. So even like if it's HVAC or vacuums, it's like the more data they have, the better. The more data they can learn
exactly,
from
yeah,
is
yeah,
makes a
yeah.
difference. Yeah, gotcha. Yeah. Next question. I don't know if the power consumption is a big deal in this application, but is there any significant power consumption difference between, let's say, a MEM cell sensor versus a fully integrated sensor?
Um, to be honest, not that big. But in the end, it's not just about the power. But then, if you are using this kind of digital systems, then you are designing your own peripheral circuitry, and if you have then you have to take care of the power consumption by yourself, and
Yep.
make sure that that consumption doesn't in, get increased, rather than using the fully integrated sensor system, because the integrated sensor system also has the benefit that for example, our sensor has a filter, so low pass filter, so we can enable it or disable it directly on the sensor level. So when I see that I don't need a higher accuracy or higher resolution, then I can turn off the filter and I
Oh
will
yeah.
have a
Okay.
better power consumption. So
Yeah. Yeah.
this is something that is a dynamic, and this would in the end benefit and also save a lot of efforts in terms of the design.
Yeah.
So
So it's
maybe
more
the
about,
power consumption. Yeah,
yeah, it's all about overall power system power consumption. You're
exactly.
worried about, not
Yeah,
the
yeah.
because these things aren't running off of batteries, so it's not really that kind of thing.
Exactly, these are not for batteries, but still, I mentioned that our sensors that we have are more or less suitable for battery operations. They are
Right. Okay.
the power consumptions are, I mean, not in microamperes, in terms of in milliamperes, in single digits, around 3 to 4.
Mhm.
So not fully suitable for battery operations, but yes, some kind of remote operation is also
Oh, good.
okay
Okay.
to have.
Good. Well, Nina, it looks like we covered all audience questions. So I want to thank you again for a great presentation, and thank you for sticking around for a good Q&A.
Sure. Thank you very much, Jeff.
Great. Okay, so before we close out this All About Sensors live session, I'd like to announce our prize winners for this session. So congratulations to Corey Fernrell and Michael Stauffer. We're going to be in touch with you in the next week to make sure that we have all the information we need to send you your All About Circuits goodies. And because this is the last session of the day, I get to announce the grand prize winner, and that is Brandon Delgado. You are a lucky prize winner, and our All About Circuits event team will be reaching out to you to make sure that you can select a prize that you truly want. In just a moment, you're going to be redirected to Worth Electronics Summit Series microsite. I encourage you to check out other live sessions and keynotes that are going to be on demand for this great event. And Nina, thank you again, and thank you, audience, for attending All About Circuits Summit Series 2025.